Imagine a future where, well, most of the aircraft flying around a naval fleet don't have pilots.
Yeah, it's not really science fiction anymore, is it?
Some analysts are saying this shift, it could happen within maybe the next 20 years or so.
Which really makes you rethink the whole idea of a traditional aircraft carrier.
It absolutely does.
And what's really striking is just how fast these unmanned systems are developing and how they could completely change naval operations.
Okay, let's unpack this then. Today, our deep dive is all about integrating these drone carrier systems.
Right.
We've been looking closely at a report that digs into how navies are adapting to this explosion in unmanned tech.
Focusing specifically on drone control, the logistics, which are incredibly complex, and, how you actually get these things working on existing ships.
Exactly. So our aim here is to pull out the really crucial insights from the report, give you a solid handle on this complex topic without getting lost in all the technical jargon.
Think of it as a shortcut, maybe.
Yeah.
Your express route to understanding what might just be the next big thing in naval warfare.
So our mission today, and you're right here with us, is to get to grips with the critical parts of managing drone operations from naval platforms.
Looking at the tech that's already out there, but also what's coming down the pike.
Right. So let's start with the big picture. What's driving this massive shift in naval power?
Well, connecting it to the broader trends, there are a few key forces pushing this forward.
Okay.
First, just the sheer pace of advancement in unmanned systems themselves, UXS as they're called, drones in the air, on the water, even underwater, are getting way more capable.
Right.
Second, you've got artificial intelligence. AI is letting these systems operate more autonomously, do more complex things on their own. And third, there's this big push towards networked operations, integrating all these unmanned systems into the wider naval force.
So they all talk to each other, basically.
Pretty much.
Yeah.
Which gives you better situational awareness, extends your reach, and opens up completely new ways of doing things.
Okay, this is where it gets really fascinating for me. How do you actually manage a whole group, maybe even like a swarm of these drones? It can't just be like flying one remote-controlled plane, can it?
No, definitely not. And that brings up the huge issue of command control, or C2.
Right.
Managing lots of drones.
Yeah.
Especially when you factor in that humans still need to be involved in the decision-making.
Yeah.
It's way more complicated.
Okay.
The report we looked at lays out a few different ways navies are thinking about this C2 architecture.
Like what? Give us the rundown.
Well, one way is centralized control. You can sort of picture a conductor leading an orchestra.
Okay, one person calling the shots.
Yeah, a single control point, maybe on the carrier itself, sending out commands, processing the info for every drone. The upside is it seems simpler to coordinate.
Seems simpler.
Okay.
But
That simplicity hides a pretty big weakness. A single point of failure could take out the whole fleet.
okay, like putting all your eggs in one basket.
Exactly. It's a reminder that those old hierarchical structures might not work so well against modern threats. Plus, it could get overwhelmed with data if you have really large swarms. Latency could become an issue.
Right. Makes sense. So what's the alternative?
Then you've got decentralized control. This is where the drones are more self-sufficient.
Okay.
They operate based on local information. They gather themselves, following preset rules and coordinating with drones nearby.
So more like a flock of birds or a school of fish.
That's a great analogy, yeah. The big advantage here is resilience. No single point of failure. And it scales up better for bigger numbers.
But the catch?
The trade-off might be less direct control or oversight from a central commander.
Okay. And you mentioned a third way.
Yes, distributed control. This tries to find a balance between the other two.
How so?
Think of it like a really good sports team. Everyone knows the game plan. They can make their own decisions in their area, but they're constantly communicating, coordinating to win together.
Okay, like shared decision-making.
Exactly. It's more consensus-based.
Yeah.
Each drone has some autonomy, but they collaborate closely, sharing info to reach the common goal.
So kind of a mix of top-down direction and bottom-up action.
You could put it that way, yeah.
Now, AI, artificial intelligence, I know that's a huge part of this.
Yeah.
How does AI fit into actually controlling these swarms?
Well, AI is really the game changer here, particularly things like artificial neural networks and deep reinforcement learning.
Good.
These allow the drones to actually learn and adapt their behavior in really complex, changing situations.
So they get smarter on the fly?
In a sense, yes. It massively boosts their ability to make autonomous decisions and coordinate with each other. Makes the whole swarm much more adaptable and efficient.
It sounds like something out of, well, a sci-fi movie. But all this coordination, all these decisions, they need really solid communication networks,
Oh,
right?
absolutely critical. The report really stresses that.
Mm.
You need incredibly fast, incredibly accurate information flowing back and forth.
And that's where things like 5G come in.
Exactly. Advanced communication tech like 5G with its higher speed and data capacity is going to be essential for making these sophisticated drone control systems work reliably.
Okay, so we have these potentially autonomous swarms, but the report also talked about human intelligence-backed operations. Where do people actually fit in? Or are we just going to be watching robot fleets do everything?
No, not at all. The report is very clear on this. Human involvement is still absolutely critical.
Especially for complex missions, I imagine.
Exactly. Or when things go wrong, when the unexpected happens. The report breaks it down into 3 main levels of human involvement.
Okay, lay them out for us.
First, you have human in the loop, or HITL. This is pretty much how things work now with many remotely piloted aircraft.
So the operator is directly flying it, making all the key calls.
Precisely. Direct human control, especially for things like releasing weapons. Then there's human on the loop, HOTL.
Okay, what's different there?
Here, the human acts more like a supervisor for multiple autonomous or semi-autonomous drones.
Ah, so the drones do the routine stuff.
Right. They handle navigation, maybe initial searching, but they alert the human operator for the big decisions, like, hey, I think I found a target, what should I do? Or permission to engage. The vision is maybe one operator overseeing 7, maybe even more, UAVs.
Wow, that's a huge force multiplier right there.
Okay, and the third level.
That's human out of the loop, or HUTL.
Sounds concerning.
Well, this is where the AI-powered drone carries out the entire mission, potentially including lethal action, completely on its own, maybe just reporting back after the fact.
Yeah, you can see the ethical considerations there.
Absolutely. Significant concerns, which is why the approach, especially in the West, is generally very cautious about HUTL.
Okay. Now, the report mentioned a specific system, cohesion. What's that?
Ah, yes. Thales' cohesion demonstrator. It's a really good example of that supervised autonomy, that human-on-the-loop model we just talked about.
So how does it work?
The idea is that AI and intelligent agents handle a lot of the workload processing data, suggesting actions which reduces the mental strain on the human operator. But the human is still in charge.
Absolutely. The human stays firmly in control, especially for those critical decisions. And operators can even adjust the level of autonomy on the fly, depending on the situation.
Flexible autonomy.
Exactly. Their guiding principle is trusted, cybersecure, human-in-the-loop AI. It ensures the human is always there for the important calls. And it really is a force multiplier, because the drones can do a lot of the sensing, the sharing, the initial analysis, all under human supervision.
That sounds like a smart way to leverage AI without losing that crucial human judgment. Okay, the report also listed some specific C2 and swarm management systems. Can you give us a quick tour of the key ones relevant for naval ops?
Sure. Let's start with Kratos UVCS. This is a system used by the U.S. Navy and Army for unmanned missions across air, land, and sea.
Versatile.
Very. It can manage multiple vehicles, allows for both manual and autonomous control, and can integrate different payloads, even electronic warfare systems. And crucially for swarms, it has an open architecture, supports multiple data links, and can operate several vehicles at once.
Okay, Kratos UVCS. What else?
Next up, Drone Shield Drone Sentry C2. Now, its main job is actually counter-UAS, defending against hostile drones.
Right.
But it's interesting because it excels at sensor fusion, blending data from lots of different sensors. And it provides a really intuitive interface for situational awareness. Plus, it supports common APIs, which means it can talk to other systems easily.
Application programming interfaces, like standard plugs.
Exactly. So it could potentially integrate with existing naval systems like ATAC, the Android Team Awareness Kit, and share data using standard formats like JSON.
So even though it's for defense, the tech could help manage our own friendly drones too.
That's the idea, yes. Then there's Stratomap's Drone Delivery Dispatch.
Sounds commercial.
It is, primarily for drone delivery logistics. But the relevant part is its focus on optimization for large-scale dispatch.
Ah, planning routes and schedules for lots of drones.
Precisely. It handles things like weight, volume, time windows, distance, all critical factors when you're trying to launch and recover maybe dozens of drones efficiently from a carrier deck.
Interesting parallel. Okay, what about swarm control from Northeastern University? The name sounds promising.
It does, doesn't it?
Yeah.
This is a software framework specifically for controlling UAV wireless networks and enabling swarm behaviors.
Okay.
It uses distributed optimization, so the drones work things out amongst themselves to some extent, but it still gives a central operator oversight.
Yeah.
It's designed to be self-organizing and adaptive.
Which sounds vital for keeping comms working within a swarm, especially if they're operating from a moving ship in a tricky environment.
Absolutely essential.
Hmm.
We also mentioned Thales Cohesion again, and their open robotics system.
Right, the supervised autonomy one.
Yeah, Cohesion focuses on that AI-powered supervised autonomy for swarms. Open robotics is broader, about integrating various unmanned assets using AI into those human-in-the-loop mission systems. Both aim to multiply force effectiveness while easing the operator's cognitive load.
Less brain strain for the humans, more work for the robots. Got it. And one more.
The last one mentioned was L3 Harris Amorphous. This one's particularly interesting.
Why is that?
It's an open architecture system designed to potentially handle thousands of autonomous assets at the same time,
Thousands. Wow.
including leaderless swarms. It emphasizes collaborative autonomy, smooth handover of control between operators or systems, and it's built to work with all sorts of sensors and weapons, specifically to avoid being locked into one company's products.
Okay, so looking across all these different systems,
Right.
what's the common thread? What capabilities are most important for naval drone carriers?
The report really points towards systems with open architectures that's key for flexibility. Also, advanced AI for autonomy and collaboration within the swarm. And, crucially, explicit support for managing multiple vehicles, potentially swarms, in contested environments where communication might be jammed.
And they need to plug into existing Navy systems, presumably.
Absolutely. Integration and interoperability are non-negotiable.
Okay, you've hit on open architectures and interoperability quite a bit. Let's dig into why those are so fundamental for building a naval drone force.
Right. Well, just think about how complex a modern naval fleet already is, right? Ships, planes, subs, all with their own systems.
Yeah, a system of systems.
Exactly. Now, layer on top of that potentially hundreds of drones, maybe from different companies. If they can't talk to each other, if they're all using proprietary software and different radio protocols, you end up with chaos, a fragmented, inefficient mess.
Like trying to build something where none of the parts quite fit together?
Precisely. So open architecture systems like the L3 Harris Amorphous or Kratos C2 we mentioned are designed to avoid that. They let you integrate tech from different vendors.
So you're not locked in.
Exactly. You can pick the best tool for the job regardless of who makes it. The Navy's own Common Control System initiative is pushing hard in this direction too.
And what about those standardization agreements, STANAGs? How do they help?
STANAGs, like the NATO STANAG 4586, are super important. They define common rules, architectures, interfaces, data formats, communication protocols, specifically for controlling UAVs.
So everyone speaks the same basic language.
That's the goal. It means different UAV systems, even from different allied countries, can work together much more easily. Companies like CUDA Technologies and AeroVironment make STANAG 450-586 compliant gear.
Like translators.
CUDA provides software that acts like a translator, yes, converting proprietary messages into the STANAG standard. AeroVironment offers ground control stations that are already compliant, and their JUM-MP-20X drone supports it too.
Okay, so STANAGs create a common control language.
Right. And then you have things like API support, which we saw with Drone Shield, standard ways for software to connect and exchange data. Even Anduril's Lattice OS, their AI platform, while maybe less open publicly about third-party APIs, represents this idea of system integration software.
So the big takeaway is...
The big takeaway is that building a multi-vendor drone fleet is a huge integration challenge. You absolutely need a strategy built around open standards to tackle the complexities of C2, data formats, comms, and of course, cybersecurity.
Cybersecurity. Yeah, networking hundreds or thousands of robots sounds like a hacker's dream or maybe nightmare. Before we get to that, though, how do these drones actually cooperate? The report mentioned collaborative mission autonomy. What is that?
Right. Collaborative mission autonomy, or CMA. It's the idea that multiple UAVs don't just operate near each other, but they actively work together in a coordinated way to achieve common goals.
So, true teamwork, not just flying in formation.
Exactly. It's a big step up in effectiveness. The report outlines what's needed technically for CMA.
Like what?
Okay, first, they need really solid communication and coordination capabilities, sharing data in real time, planning together. Second, each drone needs autonomous decision-making ability to analyze stuff, predict outcomes, adapt. Third, advanced sensors are key for gathering data and spotting targets or obstacles. Fourth, sophisticated route planning and obstacle avoidance is a must. And finally, redundancy and safety systems are crucial.
Wow, that sounds incredibly complex to actually make work reliably.
It is complex. But it enables some really powerful concepts, like Manned-Unmanned Teaming, or MUMT.
Where piloted aircraft work with drones?
Exactly. The Loyal Wingman, or Collaborative Combat Aircraft, CCA concept, is a prime example. You have AI-driven UCAVs flying alongside manned fighters.
Doing what? Carrying extra missiles?
That, yes, but also providing extra sensors, electronic warfare support, acting as decoys, potentially at a lower cost and risk than another manned aircraft. We're also seeing swarm tech being explored for logistics, synchronized deliveries, again, all relying on that fast, reliable information sharing.
So these drones can sense, decide, and act together almost like one organism. Mind-blowing. Now, back to the humans. How does that human-in-the-loop idea work with a whole swarm? Trying to micromanage 100 drones sounds impossible.
You're absolutely right, it is impossible. Direct control one operator per drone in a large swarm, that's just cognitive overload waiting to happen.
So how do you manage it?
That's where the human-on-the-loop or supervised autonomy model really comes into its own for swarms.
The supervisor role again?
Exactly. One operator might oversee, say, 7 or more drones. The drones handle the routine stuff, flying the pattern, scanning an area autonomously.
And they only call the human when needed.
Precisely. They alert the operator for critical decisions. Target identified, request confirmation, or permission to engage. Thales cohesion, again, is built for this, letting operators even adjust the autonomy level. The goal is multiplying force without overwhelming the person in charge.
So it's about setting the strategy, defining the rules of engagement, and then stepping in for the crucial calls.
That's a good way to put it. And just to reiterate, the human out-of-the-loop model, where the AI makes all the calls, including lethal ones, that's the one raising major ethical questions, and where development is proceeding very cautiously.
Understandably.
Systems like Thales Open Robotics stress that human judgment has to remain central, especially for lethal force, aligning with principles like trusted, understandable, and ethical AI. You need really intuitive C2 interfaces so operators know what the swarm is doing and can intervene easily when necessary.
Okay, so we've got the drones, the control systems, the human oversight. Now, the really practical bit. How do you get potentially hundreds of these things launched and recovered from a naval vessel, especially a carrier? You can't just, I don't know, toss them overboard.
No, definitely not. That's a huge logistical and engineering challenge. We're talking about either adapting existing carriers, like the Ford class, or maybe even designing totally new, dedicated drone carriers.
Right.
And that impacts everything. Launch and recovery gear, how you manage the hangar and flight deck, the C4ISR systems, even handling weapons for armed drones.
Let's start with retrofitting. What would need to change on a Ford-class carrier to handle a big drone fleet?
The report points to several key areas. First, launch and recovery. The Ford already has the advanced emails, the electromagnetic catapult.
Which is good for different weights, right?
Yeah, exactly. It's smoother, handles a wider range of weights, including potentially larger UAVs, recharges faster. It's a big step up. But you might also need smaller UAS-specific electric launch systems to supplement emails, just to increase the launch rate for smaller drones.
What about VTOL drones, the ones that take off vertically?
Good point. For those, you need clear deck spots, specialized handling equipment, and likely automated landing aids to cope with rough seas and a moving deck. And for smaller, fixed-wing drones that aren't VTOL, you might use net recovery systems, though that takes up deck space and can slow things down.
So a mix-and-match approach, depending on the drone.
Pretty much. A diversified approach seems likely, using the best method for each drone type. And the big theme is automation. Automating these launch and recovery processes will be crucial to handle the sheer number of drones.
Makes sense. Okay, once they land, what about hangar space, maintenance, moving them around the deck?
That's another huge area. The report mentions concepts like dedicated unmanned vehicle carriers, or UVCs, as a possible model.
What do those studies show?
They emphasize needing on-site maintenance, refueling, rearming facilities right there to keep the drones flying as much as possible. Adapting a Ford-class hangar bay likely means rethinking the layout for potentially more, but smaller, airframes, developing new maintenance workflows just for UAVs, maybe specialized bays for batteries, swapping payloads, software updates.
And the flight deck must get incredibly crowded.
Deck cycle management gets way more complex with manned and unmanned aircraft operating together. Current procedures would likely be strained. So again, automation is key. Think of robotic tugs for moving drones, automated parking systems to maintain tempo and reduce manpower needs, and the logistics, a whole different supply chain for drone-specific parts, maybe more focus on swapping out modules rather than complex repairs at sea.
So we need highly automated, flexible spaces that can handle all sorts of unmanned systems alongside the traditional manned planes. What about the ship's brain, the C4ISR, and data links?
The Ford class has a very strong C4ISR foundation already. Advanced radars, combat management systems.
But is it enough for swarms?
Supporting large-scale drone swarms places huge new demands. You need much higher bandwidth, lower latency, and extremely resilient, secure data links.
Why?
For controlling the swarm, getting all the sensor data back, letting the drones talk to each other, especially if the enemy's trying to jam you. So upgrades to things like STACOM and Link 16 are needed, plus specialized drone links with anti-jamming AJ, low probability of intercept LPI, and low probability of detection LPD features.
Then making sure different drones can talk to the ship.
That's where the Navy's Common Control System, CCS initiative, is vital at getting those standardized C2 interfaces. It's a shift from just controlling individual drones to orchestrating whole networks of them.
Okay, so Ford class could be adapted, but it's a major overhaul. What about the idea of starting from scratch, a dedicated drone carrier?
The report explores that too. Concepts like a drone mothership or a UVC.
What's the difference?
The mothership idea is a really versatile platform supporting drones in the air, on the surface, maybe even underwater. Extending the range, acting as a hub, it would need advanced C2 for managing all those different domains. The UVC concept, often based on simulations, focuses more on maximizing drone availability through optimized support facilities, launch recovery spots, maintenance bays tailored for different drone types.
So optimized for efficiency?
Exactly. Both concepts move away from the traditional carrier, focus on big, manned, fixed-wing jets. A dedicated platform would be designed from the ground up for the unique needs of large-scale, multi-domain unmanned operations. Potentially more efficient, more capable for that specific role than a retrofitted carrier.
A fascinating glimpse into what future fleets might look like. Now, zooming back in, what kinds of drones are actually available now or soon that could realistically operate from these carriers? The report surveyed some options.
It did. For maritime surveillance and ISR, the big ones are platforms like the Northrop Grumman MQ-4C Triton.
The big global hawk derivative.
Right. High altitude, long endurance hail, flies high, stays up for ages, packed with sensors, radar, kerners, EOIR, signals intelligence, SIGINT, AI's tracking. Great for covering huge ocean areas. It's mainly land-based now, but its data supports carriers, and maybe future versions could launch via EMALS.
Okay, what about drones launched directly from the carrier?
There you have things like the AeroVironment JMP-20, especially the Marinized JMP-20X. It's a fixed-wing drone, but takes off and lands vertically, VTL. Good endurance, decent payload, and the X version has demonstrated ship launches and landings.
So organic ISR for the carrier group.
Exactly. And for smaller scale, shorter range ISR, there's the Survey Copter Aliaka VTL from Airbus, another fixed-wing VTL, easier to handle on smaller ships without catapults or nets. Generally, fixed-wing drones give you better endurance, range, and payload than rotorcraft for that persistent surveillance role.
Right, eyes and ears. What about drones that can do more, maybe strike?
Definitely. For multi-role and potential strike, you've got things like the General Atomics MQ-9B Sky Guardian.
Based on the Reaper.
Yes. Long range, long endurance, and it can carry weapons for strike missions alongside its ISR capabilities. Then you have the Collaborative Combat Aircraft CCAs, or Loyal Wingmen.
Those are the ones that fly with manned jets.
Right. AI-powered UCAVs teaming up with fighters like the F-35. Think Australia's MQ-28 Ghostbat, or the prototypes the U.S. Air Force is testing.
What roles would they play?
Carrying extra weapons, advanced sensors, providing electronic warfare support, acting as decoys. They fundamentally boost the manned aircraft's capabilities. And then there's the other end of the spectrum. Low-cost, throwaway, attack drones.
Kamikaze drones.
Essentially, yes.
Yeah.
Like the ones DIU is looking for. Relatively short range, carrying payloads for attack, EW ISR, comms relay, even in GPS-denied areas. Think Phoenix Ghost. The idea is using mass, attritable assets for swarm attacks or distributed sensing.
So the future carrier air wing looks really diverse. High-end ISR, VTOLs, loyal wingmen, maybe swarms of cheaper attack drones. What about surface drones?
Good point. The report also mentions unmanned surface vehicles, USVs, extending the fleet's network onto the water.
Like robot boats.
Pretty much. Companies like Kraken Technology Group have the K3 Scout for surveillance or perimeter defense, and the K4 Manta, which is a hybrid that can operate on the surface and submerge. Mantos has concepts like the T-12 and Devil Ray T-38 for ISRO. These could launch from or work alongside the carrier.
So it's truly multi-domain air, surface, Potentially subsurface, too, all coordinated from the carrier. Incredible. Now, for these drones to do all these different jobs, they need the right gear, the right payloads. What are we talking about?
Payload integration is absolutely key to versatility. Modularity and open systems are the name of the game.
Meaning you can swap things in and out easily.
Exactly. You've got standard sensors like regular cameras, RGB, thermal imagers, maybe multispectral or hyperspectral sensors, common on fixed-wing UAVs, but then specialized maritime payloads. The Triton's big integrated suite we mentioned, the Jetting P-20's long-range EOIR camera with onboard processing, the Aliaka's smaller EOIR and AIS.
And for the combat drones?
CCAs carry more than just sensors, extra missiles for the manned fighters, targeting pods, advanced EW jammers, or decoys. Low-cost UAS might carry small kinetic warheads, EW jammers, ISR sensors, or comms relays. Even the DARPA ancillary program is trying to boost the payload of small ship-launched VTOLs for ISR cargo.
So the trend is towards making these drones adaptable.
Definitely. That's why modularity and open systems architecture are so critical. Look at the MQ-9B's modular bays, or the JRMP-20X being open to third-party payloads. Standardized interfaces, power, data, physical mounts mean you can adapt the drone fleet quickly, integrate new tech from different vendors, tailor platforms for specific missions without designing a whole new drone. It's a huge force multiplier. Being able to swap payloads rapidly, ISR today, EW tomorrow, maybe kinetic strike the day after on the same basic drone platform, is essential for flexibility and cost effectiveness.
So a drone could shift roles just by changing its payload module. That offers incredible flexibility. Now, you mentioned electronic warfare, EW, several times. It seems like that's going to be absolutely central in this drone-filled future.
Oh, completely central. The electromagnetic spectrum is already a critical battlefield, and it gets even more complex and vital with potentially hundreds of networked drones operating in it. You need a really robust EW strategy.
Covering what aspects?
Both defense and offense. First, you have to enhance the carrier group's own EW suites to protect your friendly drones. Their vulnerabilities, their control links, their data links, their GPS navigation. You need to understand those frequencies and protocols to counter jamming or spoofing attempts.
And defend against enemy drones too, right?
Absolutely. Integrated counter-UAS or CUAS systems are essential. Things like drone shield system that can detect, identify using AI, and then jam or neutralize hostile drones. The Pentagon's JCO is pushing hard on CUAS tech interceptors, lasers, microwave weapons, EW jammers like the Leonardo DRS MLIDs. These need to be part of the carrier's layered defense.
And protecting the communication links to our drones.
Paramount. Those links are prime targets. You need advanced anti-jamming, AJ, low probability of intercept, LPI, low probability of detection, LPD waveforms, frequency hopping, strong encryption, maybe multiple communication paths. Cyber EW is also a huge threat trying to exploit those data links. So protecting your own large drone fleet requires integrating the ship's upgraded EW with dedicated CUAS and advanced data link protection. The carrier itself becomes an even bigger EW target for anyone wanting to disable its unmanned air wing.
Okay, so that's defense. What about using drones for EW offensively?
That's where things get really interesting. Drones are increasingly carrying EW payloads themselves, allowing for distributed EW effects across the battle space.
Look at the collaborative combat aircraft.
Exactly. EW is a core mission for them. They'll carry advanced jammers to degrade enemy radar, disrupt C2, protect themselves and the manned aircraft, create openings for strikes. Even those low-cost, attritable drones are being looked at for EW payloads.
Spreading the EW capability out.
Right. Using potentially hundreds of cheaper drones for distributed EW complicates the enemy's targeting problem and makes your own EW network more resilient. And it's not just aerial drones. USVs like the Mantas or the Plan 80 MUSVs can carry EW sensors or jammers, extending EW to the surface for multi-domain effects.
Where does the tech come from? Miniaturized fighter jet EW.
A lot of it, yes. Advanced systems on fighters like the F-16 Vapor Shield or F-15E EPAW show the way digital, software-defined, comprehensive suites. That tech can be scaled and adapted for larger UAVs or CCAs. And miniaturization is key, allowing sophisticated EW even on smaller tactical drones. Think compact, modular EW pods that can be easily integrated. Leonardo's Osprey AZ radar is another example of an advanced sensor adaptable for UAVs that contributes to the EW picture.
So EW is becoming decentralized, more pervasive.
Precisely. More flexible, more resilient, spread across the battle space instead of relying solely on specialized aircraft or ships. Carrier drones with these payloads dramatically boost the strike group's ability to control the spectrum.
It sounds like a constant electronic battleground. With all these networked drones relying on radio waves, how do you keep their communications operations secure, especially when the enemy is actively trying to jam or hack them?
That is a fundamental ongoing challenge.
Yeah.
UAVs are definitely vulnerable. Jamming C2 links or GPS, spoofing navigation signals or ADS-B broadcasts, eavesdropping, man-in-the-middle attacks, denial of service attacks on their systems, even malware.
Lots of ways things can go wrong.
A lot. Disrupt missions, lose control, lose the asset, or worse. So you need a multi-layered defense-in-depth approach.
Such as?
Strong access control, robust end-to-end encryption for all comms and data, spread spectrum techniques like frequency hopping, FHSS, or direct sequence, DSSS, to resist jamming and interception, anti-tampering measures to protect the drone's hardware and software, AI and machine learning for anomaly detection, spotting unusual radio signals or network behavior that might indicate an attack.
Redundancy seems key too.
Absolutely. Multiple navigation sources, GPS, Galileo, GLONASS, plus inertial sensors, maybe vision-based nav as backup, multiple communication pathways, and pre-programmed fail-safe protocols. What does the drone do if it loses contact or detects a major compromise? Return home, loiter, self-destructive carrying sensitive tech.
Are systems being designed specifically for these harsh environments?
Yes. C2 architectures like Thales Cohesion are built with degraded communications in mind, allowing drones or swarms more autonomy to continue the mission or take safe action if the link is intermittent or lost. Resilient networking tech that can adapt to interference is also crucial. DARPA has programs looking into this. Ultimately, operating effectively in a contested EM environment isn't just technical, it's strategic. It needs robust onboard self-protection, EW, secure and resilient comms, and the ability for drones to operate with increased autonomy when needed.
An ongoing technological arms race, it sounds like. Okay, one last point on EW. The report mentioned integrating third-party or existing EW systems onto drones. Why is that flexibility important?
It's about maximizing flexibility, getting the best tech for the job, regardless of who makes the drone or the EW payload. Open Systems Architecture, OSA, is the crucial enabler here.
Standard plugs again?
Pretty much. Standardized interfaces for power, data, cooling, mounts. It allows plug-and-play integration with less custom engineering, avoids vendor lock-in, makes upgrades faster. Modular payloads are part of this, easily swapping EW suites in and out of a drone's payload bay, depending on the mission.
And extending standards beyond just C2.
Ideally, yes. While STANAG 4586 focuses on UAV control, applying standardization principles to payload interfaces simplifies integrating EW gear from manufacturer A onto a drone from manufacturer B. You can also leverage tech developed for manned aircraft, miniaturize it, and adapt it for drones. The Army using Anduril's Ghost X drone shows how open systems can allow future integration of things like compact EW. It's about creating an ecosystem where you can quickly tailor and deploy the best EW capability for the current threat, requiring commitment to open standards and modular design from everyone involved.
It's incredibly complex, but the flexibility sounds game-changing. Okay, let's pull this all together. We've talked tech, C2, platforms, payloads, EW. How do we actually get there? How do we build this cohesive naval drone force operating from carriers? What's the strategic plan look like?
The report makes it clear this isn't just about buying drones. It needs a deliberate, comprehensive strategy covering tech, operations, and the organization itself.
What are the key pillars of that strategy?
First, really embracing open architectures for both the drones and the control systems. That's foundational for integrating multi-vendor systems. Systems like L3 Harry over Orphis model this system of systems approach. Second, mandating and enforcing interoperability standards like STANAG 4586 for control, and pushing for similar standards for payloads and data across different domains. Third, developing and fielding a common control system, CCS, like the Navy is pursuing, or a universal ground station, so one team can fly different drone types. Commercial systems show this is feasible.
Makes sense. Reduces training, increases flexibility.
Exactly. Fourth, having clear roles for system integrators, companies, or government teams whose job is to make sure all the different pieces actually work together reliably and securely. And fifth, taking a phased and iterative approach. Don't try to do everything at once. Start with a few key drone types in C2 systems, learn from experiments and early deployments, and gradually build up capability.
So evolutionary, not revolutionary all at once.
Pretty much. Learn as you go, adapt to new tech, manage the integration risks.
Okay, that covers the integration framework, but what are the big underlying challenges that need to be solved beyond just the drones and C2 software?
Several critical ones. Cybersecurity is massive. All that connectivity creates a huge attack surface. Needs robust encryption, authentication, anomaly detection, secure software development. Non-negotiable. Electromagnetic compatibility, EMC, on a ship is another huge hurdle.
Making sure all the radios don't interfere with each other.
Exactly. Ensuring the drones and their controls work reliably in that dense electromagnetic environment without causing problems for the ship, or vice versa. Requires careful design, shielding, testing. Then there's scaled logistics and maintenance. How do you support hundreds of diverse drones at sea? It needs a revolution in naval logistics, probably drawing on those UVC ideas, dedicated bays, automation and diagnostics, parts replacement, battery management.
And the people.
Specialized training and personnel development is essential. You need new skills, new ratings maybe for operating and maintaining swarms, AI systems, advanced payloads, EW gear, operators, maintainers, intel analysts, EW specialists, and finally, data management. PED processing, exploitation, and dissemination.
Handling the flood of data from all those sensors.
Exactly. Getting it transmitted, processed using AML, turned into actionable intelligence, and shared quickly. Needs powerful processing onboard and offboard, high bandwidth comms, smart algorithms. These enabling factors might seem less glamorous than the drones themselves, but they are absolutely critical. Without addressing them, you could have the most advanced drones in the world, but be unable to operate them effectively.
It really is a total system challenge.
Okay, but assuming we can tackle all that, what are the strategic payoffs? If we successfully integrate these large-scale drone forces onto carriers, how does that change the game in naval warfare?
The strategic implications are profound. It dramatically enhances distributed maritime operations, DMO.
How so?
Drones extend your sensor reach over vast areas, allow persistent surveillance, let you deliver effects from widely dispersed platforms, makes your forces more resilient, harder to target, better able to operate where the enemy might contest access. It means augmented lethality and capacity.
More firepower, more shooters, longer reach, ability to take on high-risk missions with unmanned assets, boosting the carrier wing's overall punch.
Yeah.
You get vastly enhanced maritime domain awareness, MDA, from all that persistent ISR from air and surface drones, better tracking, threat ID, understanding the battle space. It could also drive an evolution of carrier roles and designs.
Maybe not just traditional supercarriers.
Maybe. The air wing mix changes. Concepts like drone motherships or smaller, dedicated light carriers for drones could supplement or offer alternatives, leading to a more diverse, adaptable fleet structure. And fundamentally, it enables entirely new operational concepts. Using swarm attributes, mass, coordination, attrition tolerance for things like area denial, sophisticated deception tactics, creating distributed sensor networks, overwhelming defenses.
It really could reshape naval strategy. So wrapping this all up, based on the report and our discussion, what are the key recommendations? What should the priorities be for development, procurement, integration?
Okay, several key takeaways. First, invest heavily in open architecture C2 and integration software. That's the backbone. Prioritize systems that can handle multi-vendor, multi-domain assets, enforce standards like STANAG 4586 and push for more. Second, accelerate automated launch, recovery, and handling systems. Need high tempo, reduce manpower. Third, develop those resilient, high-bandwidth, secure data links for contested environments. Fourth, advance AI-driven decision aids to help humans manage complex swarms. Fifth, promote modular, multifunction EW payloads for distributed effects. Sixth, pursue phased carrier modernization while also seriously exploring new, dedicated drone platforms. Seventh, establish robust cybersecurity and EMC protocols from the start. And eighth, transform training and personnel development for this new era.
So it's a holistic effort.
Absolutely. It's a strategic transformation, requires a deliberate, well-funded, agile approach that balances the cool new tech with the doctrine, the logistics, the training, and practical step-by-step implementation.
Well, this has been incredibly illuminating, a real deep dive into what looks like the future of naval power. It's clear drone carrier systems, these human intelligence-backed swarms, they have absolutely transformative potential.
We've covered a lot, the C2 complexities, why interoperability is king, the changing human role alongside autonomy, the nuts and bolts of getting drones onto ships, and the critical layers of EW and cyber.
Yeah, and it leaves you thinking.
What's really thought-provoking looking ahead is how this shift with drones becoming the eyes, ears, maybe even the fists of naval power, how that might fundamentally redefine what we even mean by naval strategy, or what a fleet actually is in the coming decades.
A profound question indeed, something that goes way beyond just the technology we've talked about today.